So we've talked about intermolecular forces and the impact that they have on the vapor pressure. And I think we've developed a pretty good qualitative sense about how you would rank vapor pressure for different kinds of compounds. But we haven't gotten particularly quantitative yet in terms of explaining what's going on. I haven't thrown a whole lot of numbers at you, just a whole lot of ranking and hand waving based upon intermolecular forces. As we move into a realm of discussion that's associated with getting more quantitative, the first thing we always end up doing is thinking about temperature. Because it would make sense, if you think about it, the temperature would on some level have to impact the vapor pressure. Just taking a look at this system right here, if I decided that I wanted to increase the temperature associated with these molecules, for example, by heating them up, what would that be doing? That temperature would have the ability to impact the intermolecular forces that are sitting here, provide enough internal energy that would cause this shaking process to occur, and then the intermolecular forces would break, and I would have more gas molecules go up into the gas phase. Notice that I've upset my equilibrium. Once I turn the temperature on here, I'm no longer at a constant temperature. And because the temperature isn't constant, I'm going to see a direction in which these molecules which are going, which is toward more gas being formed. So increase the temperature, I break more of these intermolecular forces, I get more of these balls up into space, I have a higher vapor pressure. Conversely, I dump liquid nitrogen on this, and it prompts these molecules to condense by bumping into each other, falling down. They make contact with this cold solution here, they're more likely to stick, and as a result my vapor pressure goes down. Clearly, temperature impacts what the vapor pressure is. The question is, if I were to choose a temperature and say, all right, let's find steady state conditions, equilibrium conditions for that temperature, what would that vapor pressure be? In fact, those numbers I showed you before, where we were looking at mercury or looking at water or looking at benzene, those were the vapor pressures at 25 degrees. You can go look them up. Water, about 24 torr. Benzene, around 90 torr at room temperature. The question is, can I develop a quantitative model for how this works? Can I develop a model that would allow me to actually stick numbers into an equation and spit out an answer for what the vapor pressure would look like? We can, and that model is going to be built on knowing two different values: the temperature of the system that I'm working at and the actual physical parameter which best explains what is going on with these intermolecular forces. It turns out that it is the heat of vaporization, the amount of energy it takes to turn a liquid molecule into a gas molecule, that I need to know so that I can do this calculation. Now, as I begin to do this calculation, you're going to see a lot of pretty sophisticated math laid out in front of you that's ultimately going to result in me creating something called the Clausius-Clapeyron equation. But don't lose sight along the way that basically what I'm doing is deriving a mathematical expression that makes utter sense in that it suggests that there's a temperature dependence to my ability to get gas molecules into the vapor phase or to condense them, and that it's tied up in this idea of intermolecular forces. It's always good, just before actually doing some sort of fairly challenging derivation, to predict what it is that we're going to see for an answer when it's all said and done. This right here is the experimental data for the vapor pressure of water. And I wanted to show it to you now before we tried to derive the equation that was going to generate it, so you could have a sense of what was going to turn out. If I was to make a plot of temperature here versus vapor pressure, as I look at it, it seems to have this kind of feel to it. It seems to suggest that early on my vapor pressure isn't changing a lot, from 4 to 9 to 18, 19, 20. It's like it's staying fairly flat there as the temperature's going up. But then notice, once I get up to 40, 60, 80, 100 degrees, it increases exponentially. Wow. It's as if the vapor pressure increase is an exponential phenomenon. You all actually have this experience when you're at home. Suppose you got like sinus pressure or you got a cold, something like that. You go and you put some water on the stove and you heat up the water. It takes a while for the water to heat up because of that darn heat capacity being so high. But you bend over and you stick your face in front of it at room temperature and you want that vapor to come up into your face. And what do you get? Nothing. And you're waiting, and it's nothing, and it's nothing, and it's going from 20 degrees to 30 degrees to 40 degrees to 50 degrees. But there comes this point where almost, boom, like your head's down there, whoa, you get overwhelmed by vapor, and it like burns your face. And it's like, what happened? Well, what happened was there's this sort of exponential growth at a certain temperature where you go from pretty much not feeling any vapor at all to feeling a huge amount of vapor. And so that's what this data is showing us here. It's showing us that at room temperature, down here around 21, 22, 23 degrees, there's not much vapor pressure. There's not much of a head for the vapor pressure of water because of all that hydrogen bonding. It's also showing us, though, something that we can go, oh yeah, that's right. At the boiling point of water, 100 degrees Celsius, that is the definition right there, that at the boiling point, the vapor pressure that is realized is equal to the atmospheric pressure. Why? Because it is at that point that I actually have bubbles forming down inside the liquid. And I have gone from having a process which is a surface phenomenon to a process which is a solution phenomenon. So let's understand that here, that as we look at this data right here, everything up here is occurring below the boiling point, and so the vapor pressure is a surface phenomenon. But the second I get to 100 degrees, I start making bubbles inside the solution, and I now have boiling. It's no longer simply a surface phenomenon.